You know, every single time you stream a movie, fire off an email, or just scroll through your social media feed, you're plugging into this massive hidden world. It's a world of incredible power that, if you think about it, would literally melt down without constant, careful attention. So today, we're going to pull back the curtain on the huge, invisible system that keeps our entire digital lives from overheating.
And no, I'm not kidding. What actually stops the internet from melting? A modern data center is just crammed with thousands of super powerful servers, and altogether, they generate this unbelievable amount of heat. If you don't have a way to constantly pull that heat out, the whole operation would literally cook itself into failure. So, how in the world do they do it?
All right, let's dive right in. The best way to understand the solution is to actually follow the problem. So we're going to treat heat as our main character, our antagonist, and we're going to follow it on its journey, right from the moment it leaves a tiny server chip all the way until it's safely released into the sky.
Now, along the way, we're going to meet the key players in this whole drama. You can think of them as this highly specialized crew. You've got the air handlers. They're kind of like the first responders on the scene. Then you have the chillers, which are the powerful heart of the whole operation. The pumps, they're the circulatory system moving everything around. The cooling towers handle the final disposal. And watching over it all is the BMS, the central brain that coordinates every single move.
Okay, so our journey starts deep inside the data hall, right where all the action is. And the very first problem to solve is this. How do you grab all of that scorching hot air that's just blasting out of the back of thousands of servers?
Well, that is the job of the computer room air handler, or what everyone calls a CRAH. These things are absolutely enormous, and they basically act as the lungs of the data hall. See, the servers are set up in rows to create hot aisles and cold aisles. The CRAHs suck in all that hot exhaust from the hot aisle, they pull it across a big coil filled with cold water, the heat jumps into the water, and then the CRAH blows cool air back out into the cold aisle for the servers to breathe in. It's a constant cycle. And listen, we're not talking about just a little bit of warmth here. The air coming out the back of these servers can be over 100 degrees Fahrenheit. The CRAH's entire job is to wrestle that temperature all the way down to a nice, manageable 75 degrees, and it has to do it again and again, 24/7, without ever stopping. Okay, so we've captured the heat, it's out of the air, and now it's trapped in the water that's flowing through those CRAH. But now what? Well, that water gets piped out of the data hall and into a completely separate building called the chiller plant. And this is where the real heavy lifting happens.
So inside this giant machine, the chiller, a process you might remember from science class kicks in, the refrigeration cycle. It sounds complicated, but it's pretty straightforward. First, a special refrigerant gas gets squeezed, compressed, which makes it super, super hot. Second, that hot gas is used to heat up a totally separate loop of water. This transfers the heat and causes the refrigerant to cool down and turn into a liquid. Third, that liquid gets forced through a tiny valve, which makes it expand and become intensely cold. And finally, that now ice-cold refrigerant is used to absorb all the heat from our original data center water, making it chilly again before it heads back to do its job.
And this table right here, this is where you can really see that great exchange in action. Just look at the chilled water loop. It comes into the chiller warm at 56 degrees and leaves at a brisk 46 degrees. So where did that 10 degrees of heat just vanish to? Well, it didn't. It got transferred over to that condenser water loop. That water came in at 85 degrees and is now leaving 10 degrees hotter at 95, carrying away all that unwanted energy. Pretty clever, right?
So now our heat has a new ride. It's in that condenser water, but we still have to get rid of it for good. The final destination for all this waste heat is outside the building entirely, where we can just let it go.
And that's the job of the cooling towers. You've probably seen these giant structures. They work on a really simple principle, evaporation. It's the same thing that happens when you sweat. The hot condenser water is trickled down over a huge surface area while massive fans are pulling air through it. A little bit of that water evaporates, and as it turns to vapor, it carries all that heat away with it, up and into the atmosphere.
So, the heat is finally gone, released to the sky. The condenser water is cool and ready to go pick up more heat. But what about our hero, the chilled water? Let's follow it as it gets pumped all the way back to the data hall to start the whole cycle over again.
Now this is all about the pumps, and it's a great example of how this engineering just keeps getting better. The old way, which you can see on the left, was really complex. It used two different sets of pumps that kind of fought against each other, and it just wasted a ton of energy. The new way, the modern standard, is so much simpler and smarter. It uses just one set of variable speed pumps that have the intelligence to only work as hard as they absolutely need to. It's a huge, huge leap forward in efficiency.
So we've met all the big pieces of hardware. But what keeps this incredibly complex dance running in perfect time? You need a conductor. You need an automated brain that's monitoring and controlling every single component every second of the day.
And that is the Building Management System, the BMS. You can think of it as the central nervous system for the whole plant. It's this complex network of sensors and software that's constantly watching everything. It tells the chillers when to fire up, it adjusts the speeds of all the pumps and fans, and it can even automatically detect a piece of broken equipment, isolate it, and start up a backup, all without a human ever touching a thing.
Okay, so we've seen this incredible feat of engineering that goes into keeping the internet from melting. But, this isn't just a cool technical puzzle. The efficiency and the reliability of this hidden world has a massive impact on the internet you rely on every day, and honestly, on the planet we all share.
So we actually measure all this efficiency with a score. It's called PUE, or Power Usage Effectiveness. A perfect score is a 1.0, which would mean zero energy is wasted on anything but computing. Now, a truly world-class data center today can hit a PUE of 1.10. Think about what that means. For every 1 watt of power the computers are using, only a tiny tenth of a watt is being used for this entire massive cooling system we just walked through. That is a phenomenal level of efficiency.
And this chart just shows you how far we've come. Just a decade ago, a typical PUE was way up around 1.8. That means you were spending almost as much power on cooling the computers as you were on running them. The kind of engineering innovations we've been talking about have absolutely slashed that wasted energy. And finally, there's reliability. This whole system is designed for what they call 5 nines availability, or even better. To put it simply, the cooling system is treated as being just as critical as the power grid. It absolutely, positively cannot fail. Because if the cooling goes down, the internet for that whole facility just goes dark. So there you have it. This incredibly complex, super efficient, and unbelievably reliable system is the invisible engine that's cooling our cloud right now. But with the crazy explosive growth of AI, which needs servers that are hotter and hungrier for power than anything we've ever seen before, it leaves us with one really big question. What is the cooling system of tomorrow gonna look like?